Okay, we jump into chapter 9. Section 9.1 is on sequences. And the definition of a sequence is a function whose domain is the set of positive integers, even though sometimes we use whole numbers starting at 0. Okay, but whenever you see a sequence written, if it doesn't say otherwise, I would assume it starts at 1. Okay, so I'm writing this in terms of function notation, which you may not have seen before, but f is a function. This is the domain. So z is the set of integers, and the plus is saying positive integers, right? Remember, the integers are 1, 2, 3, 4, dot, 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 0, minus 1, minus 2, dot, dot, dot. So the positive integers are 1, 2, 3, 4, etc. So we're taking f of positive integers, and it's spitting out a real number, okay? So this is called the codomain, okay? So you're taking into positive integers to real numbers, okay? So this example says, suppose f of n is given by n squared plus 1. Notice we didn't write f of x. F of x, when you write that, that typically stands for the domain is all real numbers. So n, oftentimes when you see n, you think of that as a positive integer, or sometimes even just an integer. Okay, so this is a function mapping the positive integers to the real numbers. Let me just write a few values now. So f of 1, that's 1 squared plus 1, that's 2. And f of 2, 2 squared is 4 plus 1 is 5. F of 3 is 3 squared plus 1 is 10, and f of 4 is 4 squared plus 1 is 17, and you keep going, okay? So that's all a sequence is, okay? You're plugging in positive integers unless it says otherwise, and it's spitting out real numbers. Here it turns out to be integers as well. Now, just for ease of notation, instead of writing f of 1 and f of 2 and f of 3 and f of 4, which is nice notation because, function notation is nice instead of just y equals, because it tells you you're plugging in 1 to get 2, you're plugging in 2 to get 5, etc. Right? For sequences, instead of writing f of n, we often will write a sub n. So a sub n is n squared plus 1. That's the equivalent of that. So f of 1 of 2 is a sub 1 is 2. That means we plugged in 1 to get 2. Or you can think of the first term in the sequence is 2. And then a sub 2 is 5. The second term in the sequence is 5, etc. Okay? So instead of writing f of, oftentimes you will see this. And just be aware, the book is writing brace a sub n equals brace n squared plus 1, because it's really a set. But I'm just going to write this. I'm not going to write the braces. Okay? Okay, so the next definition says, a sequence is said to converge. Remember, we use the term converge in the section on the improper integrals. If you get a number answer, the improper integral converged. If you didn't get a number answer, infinity minus infinity or doesn't exist, we said the improper integral diverged. We're using the exact same language here. So a sequence converges if it approaches a limiting value. Okay? So notice you keep going, f of 1, 2, 3, 4, 5, 6. So you look for the pattern in the y values. Are they getting close to a certain number? Just like when you did limits in Calc 1, right? The limit as x approaches c of f of x was L. That meant the y values were getting close to a certain number. But notice there, x was getting close to c. Here, you keep going, okay? You just keep going to infinity. So it's like the limit as x goes to infinity. Okay. So let's look at the first example. You have 2/3. That's a sub 1 if you call the sequence a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, etc. Are these numbers 2/3, 3/4, 4/5, 5, 6, 6, 7s? If you keep going forever and follow that pattern, are they getting close to a single number? Well, notice they're getting bigger. 3/4 is bigger than 2/3, and 6, 7 is bigger than 5, 6. Notice the numerator is always less than the denominator, so those numbers are always less than 1, but they're getting closer and closer to 1, aren't they? This sequence converges to 1, right? 6 7s, 7 8s, 8 9s, 9 10s, etc. Eventually, you're going to be at 999 over 1,000. So the numbers are getting closer and closer to 1. Notice you never hit 1, but you get closer and closer. Now, what about example B? I've called this sequence a sub n is cosine n. Now, if you don't have a good feeling, what could you do? You could do like I did here and just write the first few terms. And remember, right, when you see this, we're using radians. Why don't we list a couple of terms here to see what's going on? I'm not in radian mode. Let me get in radian mode. Right? So again, a sub 1, that's cosine of 1. Notice it's not cosine of pi, it's just cosine of 1. That's about 0.54. A2 is cosine of 2, which is negative 0.416. A3, which is cosine of 3, is negative 0.998999. I'll just say 99. Let me do one more. A4 is cosine of 4 is minus 0.65. Well, it doesn't look like, excuse me, there's a good pattern there. I mean, there's nothing obvious that's going on, because notice we were positive, and then we got smaller, then we got smaller even, and then we got bigger. Now, if you think about what's happening, think about the cosine graph. Right, etc. Oh, we don't care about that end, right? We're going this way, right? So remember, 1 radian's in the first quadrant, and so cosine's positive, about 0.54. I don't know where that is. I'll just pick something. Right? And then A2, 2 radians is in the second quadrant, right? 2 radians in the second quadrant, and so it was down here somewhere. 3 radians is almost 2 pi, right? And so that's the one that's, well, here. Right? And you keep going. So do you see what's happening? I mean, y equals cosine x, right? That's the graph with all real numbers x in the domain. And here we're just taking the integer. So we're just taking, sorry, part of the graph. Right, and A4 is here, right? So we're landing on this graph. Now, are these values, well, not this one, that I put here, are those going to approach a single number? They're not getting closer and closer. Look, oh, we're getting close to -1, but then we turned around. Oh, we get close to 1, but then you turn around. They're not getting closer and closer and closer and closer to a single number. So this sequence doesn't converge. I mean, this sequence diverges, right? What does this sequence do? The 2, 5, 10, 17, etc. Are those getting close to a single number? No, I mean, this n squared plus 1 is going to get bigger and bigger and bigger and bigger, so that sequence won't converge either. Now let's look at this example C here. So let me erase this. It says b sub n is -2 to the n. Again, if you don't have a good feeling for what's going on, list a few values. Now sometimes a couple of values isn't going to be enough, but you might want to do it just to get a feeling for what's going on. So b1, -2 to the first is -2. b2, -2 squared is 4. b3, -2 cubed is -8. b4, -2 to the fourth is 16, and you keep going. Now again, if you want to think of a graph, like I just did for the cosine, I mean, that may be helpful. So again, when n is 1, when n is 2, when n is 3, when n is 4, oh, I better do this. Right? Think about it. When b is 1, when n is 1, you're at -2. When n is 2, you're up here at 4. When n is 3, you're down at -8. And when b is 4, you're way up here at 16. Now, do you see what's happening? When n is odd, you're going to get a negative number. When n is even, you're going to get a positive number. So notice the pattern here is here, 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 here. Is that going to get close to a single number? No, because you keep alternating it further away from the x-axis. So the y values are not approaching a single number. So this sequence diverges too. Doesn't get close to a single number. Okay, let's look at this next example. Again, if you don't have a good feeling for what's going on, list a few values. C1 is 2/7. C2 is 2/7 squared, that's 4/49. What's happening to the fraction so far? 2/7 is quite a bit bigger than 4/49. What about C3? C3 is 2/7 cubed, so that's 8 over, well, what's 7 cubed? I should know. 343. And notice, as opposed to this example, all these values are going to be positive. 2/7 to a positive power is going to be positive. Again, if you try to plot those values, what is that going to look like? At 1, you're at 2/7, and at 2, you're at 4/49, and at 3, you're even smaller. 8/343 is tiny. So what's happening to these y values? If you keep going further down the list, the denominator is going to get a lot bigger than the numerator does as you go, right? The next one's only going to be 16 in the numerator, and the bottom one's 20, 2000 something. And so you see the y values are getting smaller, but they're always positive, so they're getting closer and closer to 0. So this sequence converges to 0. Notice you never hit 0, because you're never going to get a 0 in the numerator, because it's 2 to a positive power. But the numbers are getting smaller and smaller and smaller. Now, often I will have students, because of the example we did before with that cosine, well, if you ever have a cosine or sine, it's going to be, it's going to diverge, because of the cyclical nature of sine and cosine. And that's why I made up this example here. Let's start listing some values here for this. It does have a sign, but so sine of x. Why is sine of x is, well, this isn't the right numbers, right? It's cyclical in nature. But remember, we're not taking every x value, all real numbers, we're only taking the integers, right? Like before. But notice I've added even the 2 pi in. Well, let's plug in n equals 1. Well, what's sine of 2 pi? Well, 2 pi is 1 complete revolution, right? What's sine of 2 pi? If you use unit circle, pick the number 1 unit away, that's 1, 0. Remember, cosine is the value, as the x value, sine is the y value. Sine of 2 pi is 0. Well, now let's let n be 2. Now you're at sine of 4 pi. Well, where's 4 pi? That's 2 times around, and you're right here again, and what's the sign? 0. And sine of, let n be 3, sine of 6 pi is 3 times around, and you're right back here again, sine is 0. So all this is the sequence 0, 0, 0, 0, 0, 0 in disguise. So just because you see your sine or cosine does not mean the answer is, the sequence doesn't converge. Okay? So here, this sequence converges to 0, because it's 0 every single time. Okay? Every value of the sequence is 0. Okay, I want to skip the next definition and example so I can do that with you in person. So let me jump down to this on page 2, theorem 9.1. So you have to remind me to do those examples I skipped in class. Okay, so this theorem says, let L be a real number and let F be a function of a real variable, so f of x, like we've always done, such that the limit as x goes to infinity of f of x is L. So let me just draw a picture of what that could look like just before we read on. Okay, so x is a real number. We're not just doing the positive integers like a sequence. This is just what you did in Calc 1. Right? So here's L, say. I'm gonna put a dashed line just so we can see it. And when x goes to infinity, f of x approaches L. So, I don't care what it does back here, but eventually, say that. Suppose the function f did that. There's f of x. So, do you agree this is an example of this? This would be satisfied. When x goes to infinity, the y values get closer and closer to L. So it doesn't matter what it does, eventually, right? Beforehand, but eventually it gets closer and closer and closer to L. And notice I did cross a horizontal asymptote. There's nothing in the rule book that says you cannot cross a horizontal asymptote. Right? Even rational functions can cross a horizontal asymptote. So, okay, so there's a picture of that. Now let's read the next part. It says, now suppose we have a sequence A sub n, and the sequence is given by f sub n is A sub n for every positive integer n. So what they're saying is a sub 1 is the same as f of 1, and a sub 2 is the same as f of 2, and a sub 3 is the same as f of 3, referring to this same function here, f. So the domain of this f is real numbers, but remember for a sequence it's only the positive integers. All right, so where's the sequence in this picture? Okay, and let me just put some tick marks here. 1, 2, 3, 4. Okay. So a sub 1 is the number value for a sub 1 is the y value at 1. So there's a sub 1 right there, right there. F of 2 is a sub 2, there's a 2. F of 3 is a 3, there's a 3. And f of 4 is a 4, right, which is there. Right? So the original, my function f of x is, the graph here. My sequence are these points. 5 would be where we're here, okay? So what's the conclusion? The conclusion says if you take the limit as n goes to infinity of the sequence, you also get L. This is not earth-shattering. If your function f of x, the solid line, the solid graph here, if eventually those numbers start getting to L, and then you just pick certain points on that graph, goodness, sorry, the sequence points, aren't those sequence points going to have to start going to L? If you can't jump off of the graph, eventually the sequence points are going to go to the same thing. That's all that this is saying. And it makes sense, right? There's really nothing to prove here. I mean, it makes perfectly good sense. So if this curve, if the y values on the curve are heading to L, and you pick points on the curve and just keep going to the right, those points are going to have to get close to L too, because you can't jump off the curve. So it's an obvious theorem. Okay. Now let's look at the next example to see where this is coming into play. It says, find the limit if possible of the sequence. A sub n is 5n over root n squared plus 4. So they want us to find the limit. Well, how do you find the limit? To see if it converges, we take the limit as n goes to infinity of that, 5n over the square root of n squared plus 4. Now just think for a second what we're doing. If this were a problem in Calc 1, they would have said, here's the function 5x over the square root of x squared plus 4. And we would have taken the limit as x goes to infinity of 5x over the square root of x squared plus 4. That's what we would have done. And we would have used all the properties of limits we talked about before to figure this out. Now they're saying find the limit of the sequence. So what the previous theorem is saying, the answer to this limit problem is going to be exactly the same as the answer to this limit problem. Because every single one of these values went in as 1, 2, 3, 4, 5, 6, etc. is going to lie on the graph of this function where x, the domain, is, well, here, all real numbers. Okay? So the point that theorem is making is any rules that you were allowed to use to do this limit, you are allowed to do this limit as well, because the limits are going to be the same by the previous theorem. Okay? That's all that previous theorem is saying is, to find the limit of this, it's the same as taking the limit of this, so you can use the exact same procedure. Okay, and so I've done one like this before in here, so I'll just do exactly what I did before. Maybe I'll try something else that we haven't tried. I mean, we did this. We attempted something this in L'Hopital's rule section. Let me see if L'Hopital's rule applies. When n goes to infinity, the numerator blows up, the denominator blows up. Okay, so we can use L'Hopital's rule. Now keep in mind here. N, right, the values of n are 1, 2, 3, 4. They're single points. So you really can't take a derivative, right? Isolated points, I mean, derivative doesn't make sense because you have to take the limit as delta x goes to 0, but you're not allowed to do that. There are no points in between. But to do this, you could replace all the n's with x's and do what I talked about here, and then you can use all the derivatives you want. So notation-wise, I'm cheating a little bit because this is not a function of real numbers. But that's okay. So let's see if I'm going to apply L'Hopital's rule and we'll see if we can get the answer. If we don't, we'll just go back to stuff we did in Calc 1. So the derivative of 5n is 5. I'm using L'Hopital's rule. Now this is n squared plus 4 to the 1/2 power. So the derivative of that is bring down the half, leave the stuff alone, subtract 1 from the power, times the derivative of the stuff. Bring down the half, leave the stuff alone, subtract 1 from the power times the derivative of the stuff. Now, what happens if we simplify this? We get a 5 up here. The half and the 2 drop out, so you just get an n in the denominator. You can take the root up in the numerator, and I'm left with that. And notice the numerator is blowing up, the denominator is blowing up. If you use L'Hopital's rule again, you're just going to go back to something like this again. Okay, so I was worried that was going to happen. This was not a good strategy. All right, so forget that. We're not going to do it this way. Now I want you to realize, sometimes L'Hopital's rule doesn't get you anywhere. Notice all I did was basically switch the n and the root. And if I do it again, notice I'm going to get a 1 here, but then you're going to get the 1/2 to the -1/2 times 2n. You're just going to go back to something that looks like this. So that was a bust, which I thought it might be, but I wanted to show it to you. To show L'Hopital's rule doesn't always work. Okay, so let me go back to Calc 1 stuff. We did one like this in the L'Hopital's rule section where I didn't use L'Hopital's rule. So remember, for rational functions, the procedure is divide by the highest power of n in the denominator. But I'm not thinking of this as n squared. When n gets huge, that plus 4 is kind of negligible because you get, a billion plus 4. The 4 is doing nothing. I'm thinking of the square root of n squared as being like n. So I'm going to divide the numerator and the denominator by n. So let me rewrite it. So I'm multiplying numerator and denominator by 1 over n. We did one like this in the L'Hopital's rule section without using L'Hopital's rule. But on that problem, we were able, I think, if I remember, to use L'Hopital's rule to get the correct answer. And this one you can't. So 5n over n is 5. And then I have the square root of n squared plus 4 over n. Now, do you remember what we did in that section? In order to do some algebra here, we rewrote the n with a root. So I rewrote n as square root of n squared. Now remember, square root of n squared in general is not n. Square root of n squared is absolute value of n. But if n is going to infinity, we can assume n is positive, so the square root of n squared is the same thing as n. And now we only have, like, 2 more steps to go. Right, think of this root. A root over a root is a square root of the quotient. And what's nice about that, right, you have a single term in the denominator here. So I'm going to break this up. N squared over n squared is 1. 4 over n squared is 4 over n squared. And now we can take the limit. See, here you still say that's an infinity over infinity. I mean, so what's the answer? That's infinity over infinity. But notice that's an infinity over infinity. But once we get to here, it's 1 plus a constant over something getting huge. 4 over something getting huge is going to 0. 0 plus 1 is 1. Root of 1 is 1. And we get 5. So even though L'Hopital's rule, when we tried it, didn't work out, this procedure in Calc 1 worked out just fine. Okay, the next thing, I'm not going to write all this down. Let me just I'll write the first one. It says, these are limits of sequences. Suppose you take the limit as n goes to infinity of a sub n and get L. And suppose you take the limit as n goes to infinity of b sub n and you get k. So this is the limit of a sequence, each of these. Taking the limit of a sequence. Property 1 says, if you take the limit as n goes to infinity of an plus or minus bn. So if you add the 2 sequences together, now the step they're leaving out, they skipped a step, is this. You can take the limit of the first plus or minus the limit of the second. They didn't write that step out in the book. And then that limit is L, that limit is K. We assume that. So they're saying you can break the limit up. Now, that's assuming both the limits exist, right? If this limit's infinity, and this one's minus infinity, it doesn't make sense. You don't break it up. It doesn't make any sense. But we're assuming both limits exist, okay? L and K are numbers, okay? And the next one is if you have a constant times C, right? If you take, I'm writing them all down. Take the limit as n goes to infinity of CAN. That's C times the limit as n goes to infinity of AN. The third one is you can break up products, and the fourth one is you can break up quotients. Now, didn't we see something like this before? The limit of a sum is the sum of the limits. The limit of a constant times whatever, you can pull the C out front. Didn't we do this before? Right? I mean, we learned this property with limits early in Calc 1. Why are we doing this again? The only reason they're mentioning them is because all that stuff we did before was for functions f of x where x was a real number. A sub n, it's not a function of a real number, it's a function of positive integers. So all they're doing is making sure we realize all the properties we learned before for functions f of x are still true for sequences. But that's also coming from the theorem we did before, right? If the sequence is sitting on the function, the limits are the same. So if you just replace this with f of x and g of x, f of x and g of x, you got the same thing. Well, if the a sub n is matching your f of x and b sub n is matching your g of x, the theorem we did earlier says you're going to get the same answer. So all the theorems we did before with limits of functions, f of x, g of x, where x is a real number, say, are going to be true. Okay, so it's everything that you think is true about limits for sequences is going to be true because of the theorem we talked about with the matching the real number function. So we're good. That's all that's for. So there's nothing new there, except for it's everything we learned before is true for sequences. Okay, now let me just shift gears for a second here. Here's a definition you've probably seen in, say, a computer science class. If n is a positive integer, right? So n is an element of z plus, that's what those symbols mean. So n is a positive integer, okay? We define the following, n factorial, okay? So you read that exclamation point. It's not n, it's n factorial. It's a math definition. Okay, what do? You start with n, then you subtract one from n and multiply, subtract another one and multiply, subtract another one and multiply, etc., until you get down, to 3, 2, 1. Okay, so you start with n, subtract 1, multiply, subtract 2, multiply, keep going until you get to 2 times 1. And we call this n factorial. Now, notice this is the definition if n is a positive integer. If n is 0, we define 0 factorial to be 1. It is. That's just what it is. Now, the reason why 0 factorial is 1, if some of these theorems you have in probability, everything works out the way it should if 0 factorial is 1. I don't know if that's the reason they do it, but it's a reason that they do it. Right? Okay. So the example says evaluate each of the following. This is just easy practice. 7 factorial. Well, what's the definition of 7 factorial? It's 7 times 6 times 5 times 4, and you keep going until you get 3, 2, 1. So it's 7 times 6 times 5 times 4 times 3 times 2 times 1. Again, you don't have to put the times 1. And what is that? Is it 50, 40? 7 times 6 times 5 times 4 times 3 times 2 is 50, 40. Okay. The next one says 3 factorial. Well, what's 3 factorial? You start at 3 and you keep going until you get to 1. It's 3 times 2 times 1, which is 6. The next one says 1 factorial. Well, if I follow this, is it 1 times 0 times negative 1 times negative 2? Is that making sense? No. Now be careful. I just wrote this because this is the general form. You start at n and you stop at 1. Okay, that's what this is saying. You start at n and you stop at 1. So if I start at 1 and stop at 1, you just get 1. Okay, that's why I did this one, because if you try to use the definition, you may confuse yourself. This says start at n and stop at 1. So if you start at 1, you stop at 1, it's just 1. And then I said 0 factorial, but 0 factorial, I already said the definition of that is 1. Don't use this definition for 0 factorial. This was the definition for positive integers. What about negative 2 factorial? Negative 2 times negative 3 times negative 4 times negative 5 times negative 6 times negative 7, etc. forever? No. This definition's for positive integers. Okay, doesn't make any sense. And then, what about square root of 3 factorial? Square root of 3 is not a positive integer. Don't do that. There is a generalization of the factorials, what's called the gamma function, where you can take values of other things besides integers, but we're not worried about that. A fact, let me come back to this, to explain where this is coming from. Let me come back to the 7 factorial. What if I wrote this as 7 times 6 times 5 times 4 times 3 times 2? What is 6 times 5 times 4 times 3 times 2? Isn't that 6 factorial? Right, the factorial means just, it's the tail, right? You start with 6 and go to the tail. This is 7 times 6 factorial, isn't it? So 7 factorial is 7 times 6 factorial. Well, likewise, what if I did 7 times 6 times 5 times 4 times 3 times 2? Well, that's 7 times 6 times, that is 5 factorial. So you can always write a factorial in terms of a smaller factorial. Count down to the place you want, and then as soon as you stop, you have to put the factorial for the tail. So for example, 322 factorial is 322 times 321 times 320 times 319 times 318 factorial. Right? If I stop at 318 and don't write anymore, you put the factorial for the rest of the tail. So you can do it one place over, two place over, what do I do? 1, 2, 3, 4, 5 places over. Okay? So that's what that fact is saying. It says n factorial is n times n minus 1 factorial for n bigger than or equal to 1. Notice, if n is 0, negative 1 factorial doesn't make any sense. So n has to be at least 1 to do that. But again, it's also, I didn't put it here, but it's also n times n minus 1 times n minus 2 factorial for n at least 2. So you can always expand out as far as you want, and as soon as you stop, you have to put the factorial. Okay, now what is this for? What this is for is to simplify expressions. Now I want you to keep in mind, right now, what do we have in terms of factorials? The definition and the fact I just explained to you. Do not make up rules for factorials that we have not discussed. For example, I'll have students do 21 factorial over 7 factorial. And they'll cancel, 3. That's just wrong. I mean, we haven't we don't have a rule that does that. If we did, I would have mentioned it. Don't make up rules, okay? Factorials are strange creatures. Okay, so the example says simplify. 500 factorial over 498 factorial. Now most calculators have a factorial button on them. I mean, I have a TI 83 Plus. It's under, if you hit the math screen and move all the way over to PRB for probability, it's my number 4. So you probably have a factorial button. So you would hit 7, hit the number 7, go to where I just went under the math probability menu, hit the factorial, and then hit enter, and it'll give you the answer. The problem is, something like 500 factorial is a huge number. I don't think my calculator, it'll give me a memory error or storage error or something. In other words, the number's too big. So if you just try to, on most calculators, some of you may have a calculator that could do this by typing this in. Right? So what you do here, if your calculator can't handle large numbers like that, is do what we just practiced. Right? I take the larger expression, the larger value, which is the 500 factorial, break that one down until you get to 498. So that's 500 times 499 times 498 factorial, right? The tail, we keep going, divided by 498 factorial. Well, 498 factorial divided by 498 factorial is 1. So this is 500 times 499, and now you can type that in and get your answer, which is 249,500. Okay, so you can simplify factorials and then just type in the answer. All right, let's do another one. It's 9 factorial divided by 3 factorial, 6 factorial. I got this expression because this is something that shows up when you do combinations of items, just if you've seen those before. All right, so I'm going to take the largest value in there, which is 9 factorial, and I'm going to break it down until I either get the 3 or the 6, whichever you want. I'm going to go with the 6 because I don't have to write as much. That's 9 times 8 times 7 times 6 factorial over the 6 factorial, so those will cancel. And then 3 factorial, I'm going to go ahead and write 3 times 2. So you can do some canceling. The 6 factorials cancel. 3 goes into 9 3 times. 2 goes into 8 4 times, and I still have a 7 in the numerator. So 3 into 9 is 3, 2 into 8 is 4, I still have a 7, those cancel. And 12 times a 7 is what, 84? So not too hard. And then this part C says y minus 4 factorial over y minus 2 factorial. Now I didn't put any restrictions on y, but can you think about what values y could be here to make sense? Again, we're talking about integers, obviously. So can you think about what's the domain of that expression? Could y be 7? Sure, because you'd have 3 factorial over 5 factorial. That makes sense. What's a value y can't be? Y can't be 0 because you'd have negative 4 factorial over negative 2 factorial, which doesn't make any sense. Right? Well, what would have to be true here? Well, what would have to be true for y minus 2 factorial to make sense? This would have to be at least 0. So y has to be at least 2. But notice y equals 2 in the numerator doesn't make sense. You get a negative 2. So for both of those expressions to make sense, y has to be at least 4 here. So I didn't write it, but that's what's going to have to be true. Okay, So let's follow the same argument I used before. Which of these is the larger of the two expressions? Is y minus 4 factorial larger than y minus 2 factorial, or vice versa? If you're not sure, plug in a number for y that makes sense and see which one is bigger. For example, if y is 10, I just pick something. This is 6 factorial and this is 8 factorial. The denominator is larger. So that's the one I want to expand. I'm going to leave the numerator alone. And notice in the denominator, you start with y minus 2, and you subtract 1, that's y minus 3, because y minus 2 minus 1. And then another one would be y minus 3 minus 1 is y minus 4, and I'm going to put the factorial on that one, because I stopped writing the tail. And now your y minus 4 factorials cancel, and you get 1 over y minus 2, y minus 3. There you go. So the hard part is, first of all, thinking about domain I think is important. But here, which one's the larger of the two? Just plug in a number for y and see which one's larger. Okay, let me do one more example with the factorials here. The sequence is a sub n is n plus 1 factorial over n factorial. So it says determine the convergence or divergence of this sequence. Now, how do you figure out the convergence or divergence of a sequence? You take the limit as n goes to infinity of the sequence. Right? That's how you do convergence or divergence of a sequence. Take the limit as n goes to infinity. Well, it's a quotient just like we had over here. That's why I did those examples to lead up to this. We want to simplify this. Notice the numerator's blowing up and the denominator's blowing up. You might say, hey, let's use L'Hopital's rule. You can't use L'Hopital's rule here because writing f of x equals x factorial, say that one, doesn't make sense for real numbers, right? Pi factorial, square root of 2 factorial. So this is a situation where you can't actually use that theorem about, well, if it's a sequence, you can just go back to the function f of x and do everything we did before. You can't do that here because f of x equals x factorial doesn't make sense if x isn't, a whole number, 0, 1, 2, 3, etc. Okay? So we can't do that here. So you can't use L'Hopital's rule because the derivative of the factorial doesn't make any sense. Okay, so what can we do? Let's do the reduction. Which of these expressions is larger, the numerator? So I'm going to break that down. N plus 1 factorial is n plus 1 times n factorial. I stopped right away because I hit n factorial. And when you cancel the n factorials, you get the limit as n goes to infinity of n plus 1. And when n goes to infinity, what happens to n plus 1? That blows up. So it looks like this sequence diverges. We didn't get a number answer. Okay, so that's the first part of this section. We'll finish the second part in another video.